In this video, we will discuss two-way ANOVA. Data sets with two factors. The table below is an example of pulse rates, beats per minute, categorized with two factors. Age bracket in years. One factor is age bracket, 18 to 29, 30 to 49, and 50 to 80. The second bracket is gender, female or male. The subcategories in the tables are called cells. So the table has 6 cells containing 10 values each. In analyzing the sample data in the table on the previous slide, we have already discussed one-way analysis of variance for a single factor. So it might seem reasonable to simply proceed with one-way ANOVA for the factor of age bracket and another one-way ANOVA for the factor of gender. But that approach wastes information and totally ignores a very important factor, the possible effect of an interaction between the two factors. There is an interaction between two factors if the effect of one of the factors changes for different categories of the other factor. As an example of an interaction between two factors, consider food pairings. Peanut butter and jelly interact well, but ketchup and ice cream interact in a way that results in a bad taste. So we rarely see someone eating ice cream topped with ketchup. In general, consider an interaction effect to be an effect due to the combination of the two factors. Let's explore the data in the table by calculating the mean for each cell and by constructing a graph. The individual cell means are shown in the table below. Those means vary from a low of 64.8 to a high of 82.2, so they vary considerably. The figure below is an interaction graph, which shows graphs of the means from the table on the previous slide. We can interpret an interaction graph as follows. An interaction effect is suggested when the line segments are far from being parallel. No interaction effect if the line segments are approximately parallel, as in the figure above. It appears that the different categories of the variable have the same effect for the different categories of the other variable. So there does not appear to be an interaction effect. Instead of relying on subjective judgments made by examining tables and graphs, we will proceed with the more objective procedure of two-way analysis of variance. In the next several slides, we'll look at the key elements for two-way ANOVA. The procedure is summarized in figure 12.4 on page 585. Requirements. Normality. For each cell, the sample values come from a population with a distribution that is approximately normal. This procedure is robust against reasonable departures from normal distributions. Variation. The populations have the same variance sigma squared or standard deviation sigma. This procedure is robust against reasonable departures from the requirement of equal variances. Sampling. The samples are simple random samples of quantitative data. Independence. The samples are independent of each other. This procedure does not apply to samples lacking independence. Two-way. The sample values are categorized two ways. This is the basis for the name of the method, two-way analysis of variance. Balanced design. All of the cells have the same number of sample values. This is called a balanced design. This section does not include methods for a design that is not balanced. Procedure for two-way ANOVA. Interaction effect. In two-way analysis of variance, begin by testing the null hypothesis that there is no interaction between the two factors. Use technology to find the p-value corresponding to the following test statistic. F equals ms interaction over ms error. Conclusion, reject if the p-value corresponding to the above statistic is small, such as the less than or equal to 0.05, and reject the null hypothesis of no interaction. Conclude that there is an interaction effect. Fail to reject if the p-value is large, such as greater than 0.05. Fail to reject the null hypothesis of no interaction between the two factors. Conclude that there is no interaction effect. Row and column effects. If we conclude that there is an interaction effect, then we should stop now. We should not proceed with the two additional tests. If there is an interaction between factors, we shouldn't consider the effects of either factor without considering those of the other. If we conclude that there is no interaction effect, then we should proceed with the following two hypothesis tests. Row factor. For the row factor, test the null hypothesis H0. There are no effects from the row factor. That is, the row factor are from populations from the same mean. Find the p-value corresponding to the test statistic F equals ms rho divided by ms error. Conclusion. Reject if the p-value corresponding to the test statistic is small, such as less than or equal to 0.05. Reject the null hypothesis of no effect from the rho factor. Conclude that there is an effect from the rho factor. Fail to reject if the p-value is large, such as greater than 0.05. Fail to reject the null hypothesis of no effect from the rho factor. Conclude that there is no effect from the rho factor. Excuse me. Column factor. For the column factor, test the null hypothesis H0. There are no effects from the column factor. That is, the column values are from populations with the same mean. Find the p-value with corresponding to the test statistic F equals ms column divided by ms error. Conclusion, reject if the p-value corresponding to the test statistic is small, such as less than or equal to 0.05. Reject the null hypothesis of no effect from the column factor. Conclude that there is an effect from the column factor. Fail to reject if the p-value is large, such as greater than 0.05. Fail to reject the null hypothesis of no effect from the column factor. Conclude that there is no effect from the column factor. Given the pulse rates in the table at the beginning of the section, slide 2, page 586, use two-way analysis of variance to test for an interaction effect, an effect from the rho factor of age bracket, and an effect from the column factor of gender. Use a 0.05 significance level. Requirement check. For each cell, the sample values appear to be from a population with a distribution that is approximately normal, as indicated by normal quantile plots. The variances of the cells, 100.3, 51.7, 103.5, 183.2, 138.5, and 293.5 differ considerably, but the test is robust against departures from equal variances. The samples are simple, random samples of subjects. The samples are independent of each other. The subjects are not matched in any way. The sample values are categorized in two ways, age bracket and gender. All of the cells have the same number of sample values, 10. The requirements are satisfied. The calculations are quite involved, so we use technology. The StatCrunch two-way analysis of variance display for the data is shown here. Interaction effect. We begin by testing the null hypothesis that there is no interaction between the two factors. Using the StatCrunch display in the previous slide, we can see that the test statistic for the interaction is F equals 0.9391. This test statistic can be calculated as follows. F equals ms interaction over ms error, which is equal to 136.26667 divided by 145.11111, which is equal to 0.9391. Interpretation. The corresponding p-value is shown in the StatCrunch display as 0.3973, so we fail to reject the null hypothesis of no interaction between the two factors. It does not appear that pulse rates are affected by an interaction between age bracket and gender. There does not appear to be an interaction effect. RowColumn effects. Because there does not appear to be an interaction effect, we proceed to test for effects from the row and column factors. The two hypothesis tests use these null hypotheses. H0, there are no effects from the rho factor, that is, the rho values are from populations with equal means. And H0, there are no effects from the column factor, that is, the column values are from populations with equal means. Rho factor. For the rho factor, age brackets, we refer to the preceding StatCrunch display of results to see that the test statistic for the rho factor is F equals 1.8156 when rounded. This test statistic is calculated as below. Conclusion, the corresponding p-value is shown in the StatCrunch display as 0.1725. Because that p-value is greater than the significance level of 0.05, we fail to reject the null hypothesis of no effects from age bracket. That is, pulse rates do not appear to be affected by the age bracket. Column factor. For the column factor, gender, we refer to the preceding StatCrunch display of results to see that the test statistic for the column factor is F equals 13.5914 when rounded. This test statistic can be calculated as below. Conclusion, the corresponding p-value is shown in the StatCrunch display as 0.0005. Because that p-value is less than the significance level of 0.05, we will reject the null hypothesis of no effects from gender. Pulse rates do appear to be affected by gender. Interpretation: on the basis of the sample data in the table, we conclude that pulse rates appear to be affected by gender, but not by age bracket and not by an interaction between age bracket and gender. Caution: two-way analysis of variance is not one-way analysis of variance done twice. When conducting a two-way analysis of variance, be sure to test for an interaction between the two factors.